Okay, let's talk about functions today. Um, Relations and functions. So, first off, the learning goal for today is we're going to determine whether relations between two variables are functions. So we're going to have functions and relations. A relation is just, well, we'll talk about it in a second. We're going to use function notation. Hopefully you know f of x, how to use function notation. We're going to talk about the domain of functions. We'll do some real-world application, hopefully. And we'll evaluate difference quotients. We probably won't do much with difference quotients, and I probably won't test you over this either. But okay, so an introduction to functions. First of all, we're going to, anytime there's a relationship between two quantities, we're going to call that a relation. Okay, anytime, like, for example, your height and your age are related. Right, those are numbers that we could relate. We can make a formula of some sort that's pretty close to, describing that as you get older, you grow, right? So we're going to call these relations. Now, some of these relations we'll call functions. The definition of a function is a function f from a set A to a set B. Set A we're going to call the domain. Set B we'll call the range. So there's inputs for A and outputs for B. Is a relation that assigns each element x in A to exactly one element y in set B. The key is that there's exactly one element. I'll describe that more. Okay, the domain is the inputs and the range is the outputs. So here's a diagram of what a function looks like. It doesn't matter. This could be the time of the day and the temperature. So, at 1 p.m. it's 9 degrees Celsius. At 2 p.m. it's 13 degrees. At 4 p.m. it's 15 degrees. At 3 p.m. it stays 15 degrees. At 5 it's 12 degrees. And 6 it's 10 degrees. This would be a function. All right, what would not be a function is if you had this situation where at 4 it was 9 degrees and 15 degrees. That wouldn't make any sense. You can't have at 4 p.m. you can't have it be two different temperatures. That would not be useful to us. That would not be a function. This would be a relationship of numbers. We've related numbers together somehow, but it's not necessarily a function. So the key definition for a function is that each input can have only one output. That's important. Okay, now let me explain that a little bit better because it gets a little confusing. Here's our order. If I can list these temperatures as ordered pairs, these points as ordered pairs, we can look at a vertical line test through here. So the characteristics of a function, each element in A must be matched with an element in B, which it is here. Each element in A is matched with an element in B. Some elements in B may not be matched with any element in A. We don't have that situation, but that's okay. Two or more elements in A may be matched with some element in B. So that's fine. We have 3 and 4 are both matched with 15 degrees. That's okay. You can have two different x values with the same y value. You just can't have one x value with two different y values. And the best way I think I can explain this is to look at a graph and remember the vertical line test. So a vertical line test basically says, okay, if you look at a graph, I can't have one x value, like for example at 3 p.m. it can't be 7 degrees and 10 degrees. I can't have that situation. That doesn't make any sense. This wouldn't pass the vertical line test, right? 3 p.m. if that's your x value time and temperature is your y value, you can't have it be 3 p.m. and have two different temperatures. Okay, that violates the definition of a function. So think about a vertical line. One thing you can have at 3 p.m. and 4 p.m. you can have it be 10 degrees at both of those times. That's not it passes the vertical line. Okay, that's okay. So I like to think about the definition of function in terms of the vertical line test because that seems to be easiest. All right. We're going to represent functions in different ways: verbally, numerically, graphically, and algebraically. So let's look at some of these right here, and let's determine if these are functions. So A, this is a verbal representation. Let's determine if this is a function. Okay. A, the input value x is the number of representatives from a state, and the output y is the number of senators. Would that be a function, yes or no? Yes, it would be. In fact, that equation would just simply be y equals 2. Because there are two senators for each state, regardless of how many representatives there are. So this is just a constant function, y equals 2. In fact, that's a line that looks like this. Y equals 2, x can be anything. Just a horizontal line. that passes the vertical line test. That is a function. It's a constant function. No matter how many representatives you have, you always have 2 senators for every state. Okay, so that is a function. That's a weird one. It's a verbal model, but here would be the algebraic model. Here's a table of values. Is this a function? Yes or no? So this is not a function because we can't have one x value paired with 2 different y values, which is what we have. And if you go to graph this, you would see you can't have it be 2 and 10 and 2 and 11. That wouldn't these points wouldn't pass the vertical line test. Okay. C is a graphical model of the function, and yes, this is a function. It does pass the vertical line test. Next is function notation. Function notation, f of x equals 3 minus 2x, is what we're going to be using. So instead of y, we're going to use f of x. The advantage being that when you plug in a value, like say you want to find the value at x equals 3, I can say then f of 3 equals 3 minus 2 times 3, and I can just plug in 3. So f of 3 equals negative 3 in this case. So this notation allows us to say the value of the function at 3 is negative 3. It's a little bit better for communicating. Okay, next I want to talk about piecewise functions. This is something I'm going to need you to know as well. This wants to evaluate this piecewise function when x is negative 1, 0, and 1. Now, piecewise functions are confusing for people, but just keep in mind that we can define functions however we want. Okay? Our functions can do, whatever we want, represent any real-world situation. Math's a language, right? We can write an English sentence to say whatever we want, and we can write a math equation to do whatever we want it to do, right? To model a ball flying through the air, to predict sales for the next year. Or in this case, we have part of a parabola is, part of this function is a parabola whenever x is negative. So when x is less than 0, we have a parabola that's shifted 1 unit up, so that parabola would look like this. I don't need the right part, because I'm only graphing it when x is less than 0. And it's not defined at x equals 0, so I put an open circle there. At x equals 0, it jumps to this line, which has a slope of 1 and a y-intercept of negative 1. So that would be this line, slope of 1 and a y-intercept of negative 1. Okay? And that would be a closed circle right here, because at 0, it is this line. So at 0, it's negative 1. Here's what the graph would look like. We can actually graph piecewise functions in the calculator as well. So if you want to graph this piecewise function, what you do is you graph the function, then put divided by, in parentheses, this test, x less than 0. How you do that is you just obviously do divided by, parentheses, and then x. And then this less than symbol is under test right here, your second math, and click less than, 5, less than 0. Now what this test does is the calculator says, okay, is x less than 0? The calculator sticks in a number here. If that number is less than 0, the calculator puts a 1 in for this value. And so it just graphs this. But whenever x is not less than 0, it puts in a 0 here. And this function divided by 0 is undefined. So it'll be undefined to the right. So it'll just graph this branch. Now in your other y equals, you can do the same thing. You can put in x minus 1, divided by, and then do, for whenever, in parentheses, whenever x is greater than or equal to. So do second test, greater than or equal to is 4, 0. And now it'll graph that starting here all the way to the right for this line. So this is what the piecewise function looks like in your calculator. So you can do it by hand or with the calculator. This one wants you to just evaluate when x is negative 1, 0, and 1. So when x is negative 1, we're talking about being less than 0, so we're going to use it here. Negative 1 squared is 1, plus 1 is 2. So f of negative 1 equals 2. F of 0 is when it's equal to 0, so down here now is negative 1. And f of 1 is greater than 0, so that's here, that's 0. Okay? The nice thing is about having it in your calculator is you can do this in the calculator by doing second calculate value. All right, second calculate value at 1 gives you, well, actually, I need to tell it what function to go to, so I'm going to hit up to this function. 1 gives you 0. Okay. Second, calculate value at 0. I need to scroll to the other function, this one right here, because it's defined on this one only, which is negative 1. Second, calculate value at negative 1. I want to be on the parabola, which gives me 2. So it gives me these answers right here. as well. All right, let's talk about domain. All right. Domain, here's two functions I want to look out for the domain. The domain is all of my input values, so it's any numbers that I can stick in for x. So let's look at two situations. The two situations you need to look out for is when you have a fraction and a variable in the denominator. And the other situation you need to look out for is when you have a variable underneath a radical. So the domain for this first function is all real numbers, but x cannot be equal to 2 or negative 2. Because if I stick in negative 2, this gives me 0 on the bottom. If I stick in positive 2, it gives me 0 on the bottom, which we can't divide by 0. It's undefined. So these are the two places that I cannot stick in a number at 2 and negative 2. I won't get an answer. Now for a radical function, like this one, I can't have negatives underneath the radical. So basically I want all positive real numbers, or you could say x has to be greater than or equal to 0. 0 is fine. 1's fine. 2's fine, obviously, but you can't go negative 1, negative 2. All those negative numbers, you can't take the square root of them because those are imaginary numbers. So I would write that as an interval from 0 to positive infinity, like this. I would like you to use an interval, please. All right, so here's some more we could practice for finding the domain. The domain of these functions right here. Sometimes I'm just going to list points and ask you to give me the domain. So the domain would be negative 3. You know, you could just list these points. Negative 1, 0, 2, 4. Those are all the inputs, x values. I could ask you for the domain of this function, which is obviously all real numbers, except for x cannot be negative 5. Okay? The volume of a sphere, I can talk about the domain for this one, would be all positive real numbers, right? I don't want to stick in negatives because we're specifically talking about the sphere, in which case the radius can't be negative. So I would say r is greater than or equal to 0, or 0 to infinity, including 0 is fine, I guess if you have a radius of 0. There's no volume. All right, the last one would be this one. This one's a little bit more difficult. I'm trying to find the domain of this function right here. This is a square root function. You can graph it and try to look at what numbers are available, but you know that basically this 4 minus 3x, this has to be greater than or equal to 0. Would you agree? Because if it's less than, then I have an imaginary number underneath here. So let's solve this inequality, and that will be our domain. Subtract 4 from both sides. Negative 3x is greater than or equal to negative 4. Divide both sides by negative 3. When I divide by a negative, I have to switch the sense of the inequality. So this has to change, and this becomes 4/3. So my domain is all values that are less than or equal to 4/3, which as an interval, negative infinity to 4/3. I can include 4/3, don't include negative infinity. So I prefer, I guess, you write an interval notation because this seems to be what students are struggling with. But this is okay. I can stick in any number that's less than 4/3 into this, and it'll give me a positive number underneath the radical. But if I stick in a number that's too big, like for example 2, x equals 2 won't work. It's bigger than 4/3, and when I stick it in, I get a negative number underneath the radical, and I can't have that. Okay, let's take a look at one application then of these functions. Let's write a function for this this cylinder right here, this can. First of all, I'm going to want you to write a function for the volume as a function of radius. Now, volume of a cylinder, if you remember from geometry, is area of the base times the height. So it's cross-sectional area here in the bottom multiplied by the height. Now, the area of the base is a circle, so it's pi r squared times the height. So this is the volume formula for a cylinder. Now I'm going to tell you in this situation, this relationship right here, that the height is 4 times the radius. So this height right here is always going to be 4 times the radius of the can. I'm going to tell you that as well. What I want you to do is do two things. First, write the volume of the can as a function of the radius only. Okay. Then I want you to write the volume of the function as a function of h only, the height only. So you're going to have to use these two equations to eliminate variables and rearrange. Why don't you guys try that, and then I'll put the answers up. All right, if you plug in 4r in for h, you get pi r squared times 4r. Rearrange, order doesn't matter, and you get this. So this is the formula for volume in terms of radius. All right, so if you rearrange, you get r equals h over 4. Go ahead and plug that in here for r, h over 4. Make sure you square it, then simplify, and you get the volume in terms of the height is pi h squared over 16. Okay, I hope this helps.